In this video, we're going to discuss valence electrons. Valence electrons basically are the electrons farthest from the nucleus. They have the most energy, and because they're on the outside of the atom, they are the electrons that determine how a certain atom will interact with another atom or molecule. Before we get started, a reminder, the atomic theory was developed over many years with different scientists being involved. What we're going to focus on today is the Bohr model of the atom. Niels Bohr said that there were certain electron orbits, and that in each orbit there were a certain number of electrons that could be there, and then that orbit would be filled. That sounds kind of confusing, but I think I can make it make sense. So if you have an atom of argon, argon is number 18 on the periodic table. Number 18 on the periodic table means that it has 18 protons, or 18 positive charges in the core, in the nucleus. But it also means, because it's an atom, it's going to be neutral. So it's going to have 18 positive charges and 18 negative charges. Niels Bohr said that if you have the first energy level closest to the nucleus, it can hold 2 electrons, and then it's filled up. So once there are 2 electrons in this first energy level, we overflow into the second energy level. And in that second energy level, we can have 8 electrons, but then that energy level is full. And then we go to the third energy level, where we can also have 8 electrons, and then it is full. If we go past number 18, or argon, on the periodic table, we have to add more and more energy levels. But for our purposes and understanding how valence electrons work, we're not going past number 18. So I'm going to give you a couple of examples. If, for instance, we look at argon, argon has this outer energy level. Because it has 3 energy levels, the third energy level is the outside energy level. That's where the valence electrons are. That means that argon has 8 valence electrons. But if we take something like lithium, lithium is number 3 on the periodic table. So it has 3 protons in its nucleus. And in the first energy level, it has 2 electrons. But because it has 3 protons, it also has to have 3 electrons. Because this energy level is full, what I know is that that third electron is going to be out here in the second energy level by itself. So lithium has 1 valence electron, or 1 electron in its outermost energy level. Now, if we wanted to take a look at something like aluminum, aluminum is number 13. It has 13 protons, and because atoms are neutral, it has the same number of protons as it has electrons. And that means that it has 13 electrons. 2 of those can fit in the first energy level, but now that energy level is filled up. And so we have a second energy level. And here we have 8 electrons, because it can hold up to 8, and aluminum has more than 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So now we have 10 electrons on our model of aluminum. But we have 3 more electrons. So aluminum has 3 valence electrons, or 3 electrons in its outermost energy level. We're going to take a look at one more. Helium is number 2. It has 2 protons and 2 electrons. So this is what a model of a helium atom would look like. And its outer energy level also happens to be the first energy level, but it's filled up. So it has 2 valence electrons, and in this case, the number of total electrons and the number of valence electrons will be the same. The reason that it is important for us to understand valence electrons and how to calculate them is because valence electrons explain reactivity. or how an atom interacts with other atoms and molecules. So in this family, in this column, we have lithium. We just looked at lithium. Lithium has one valence electron. What that means is that it has a lot of empty space on its outermost energy level. And it's very likely to give away that other electron if it comes into contact with an atom that can take that electron from it. We'll look at that in a minute. Sodium is number 11. It also has one valence electron. And that continues through this whole family. So all of these elements, or these alkaline earth metals, are extremely reactive. They all have one valence electron on the outside of the atom, and they kind of want to give it away. They want to make sure that it's gone, because when that happens, they go back down to a filled up energy level. Over here, we have the opposite issue. So in column 18, these are the noble gases, and noble gases are non-reactive. And that's because helium, we just looked at, has two valence electrons, but its outermost energy level is filled up. It doesn't need to steal any electrons, and it doesn't want to give any electrons away. Having an outermost energy level that's filled up makes an element stable. So that's the truth for helium, but it's also true for neon. Neon is number 10. It has 2 electrons in its first energy level and 8 in the next one. But because the second energy level can hold 8 electrons, it's completely filled up. And that means it's also stable. And the same is true for argon and krypton and xenon and radon. All of the elements in group 18, or the noble gases, are stable because their outermost energy level is full. That's important, and here's why. So we're going to take a look at sodium. Sodium is number 11. Sodium has 11 protons and 11 electrons. 2 of those electrons go into the first energy level, and then in the second energy level we have 8, but that's a total of 10. So we have 1 more on the outermost energy level for sodium. And because it has all these empty spaces that I'm going to mark with little X's, it's unstable. This electron is zipping around and trying to go somewhere. But luckily, for something like sodium, if you look in column 17, these are nice little matches for something like sodium. So chlorine is number 17 on the periodic table. That means it has 17 protons and 17 electrons. In the first energy level, 2 of those electrons. In the second, 8. And then in the last energy level, it has 7, which means that it has 1 blank space. So I need for you to stop and imagine, even though we can't see these things, that if you have sodium, which is Na, and chlorine, which is Cl, and they get close to each other and there's enough energy, what can happen is this electron can be shaken loose and it jumps over here to chlorine and it fills that spot. For sodium, that means that it no longer has 3 energy levels. It just has 2. And chlorine now has a 3rd energy level that's completely filled. Now, this causes us a problem. These are no longer atoms. It has 17 positive charges, but it has gained a negative charge. So it's slightly negative. So chlorine becomes a negatively charged particle. Atoms are neutral. When we look at sodium, it has 11 positive charges and 10 negatives. So because it lost a negative charge, it now becomes slightly positive. What we now have is something called an ion. We have a sodium ion and we have a chlorine ion because they are charged. But positives and negatives, being opposite charges, attract and they will stick together. And that's why we have sodium chloride or salt. So if you have something in this area, it sticks well to things in this group. Things in this group stick well to things in this group. And the things in the middle are a little bit different. They have sort of half-filled outside energy levels. And that's where we're going to stop today with valence electrons. But hopefully that's going to make sense as we move forward.